Let's take a look at Chapter 12, Weather Analysis and Forecasting. Now, weather analysis and forecasting are two different things. In weather analysis, you're analyzing the current state of the atmosphere. With forecasting, you're going to try to estimate future weather conditions. There's a pretty good quote from Dominique Francois Arago, who said, "Never, no matter what the progress of science, will honest scientific men who have a regard for their professional reputations venture to predict the weather." Because there is so much uncertainty, you're going to be proven wrong many, many times. I've included in a few example cartoons about weather forecasters, about how they get it wrong all the time. It just seems like they're making it up. And here's some other examples of forecasting that you may have encountered. Now, a lot of people used to have a barometer where they would have a Hansel and Gretel versus the witch, where it was set up that if the barometer was low, the witch would come out, and if the barometer was high, meaning clear skies, nice conditions, then the kids would come out. I like this forecasting stone. This would be the current state of things. Of course, if the stone is wet, it means it's rain. If the stone is dry, it means it's not raining. It's casting a shadow, it's sunny. If it's white on the top, it's snowing, and so forth. So that's pretty good. And again, jokes were often made about weather forecasters getting it wrong. It seems like they're taking random guesses. That's really not the case so much anymore. The weather forecasters get it right most of the time. According to FEMA, most of the declared emergencies are weather-related. Hurricane Katrina, for example. Now, your textbook talks about the bureaucratic hierarchy of the weather business in the United States. You might not remember this 5 years from now, although I think it's encountered enough that you probably hear about NOAA images and NOAA reports and so forth for some time to come. The National Weather Service is one branch of NOAA, the National Oceanic and Atmospheric Administration, which is under the Department of Commerce. So the National Weather Service gives us weather and climate forecasts. It's also under the newly named National Centers for Environmental Prediction. Collects data from not only the United States, all over the world, and then that information is given to the WFOs, weather forecast offices. Here's a schematic breakdown of the hierarchical organization. And also on the online notes, if you take a look at those, I have some of the links so that you can go right to the Storm Prediction Center, the Weather Prediction Center, and so forth. Well, it's a hard thing to do. You have to process billions and billions of pieces of information to come up with a reasonable forecast. All right, the WMO is a world organization that's responsible for sharing this weather data. You have surface observations that are made from all thousands of weather stations across the world. The weather shelters that we've been looking at throughout the course that have the TMAX, the TMN, the hydrograph, and so forth, all of those things are standard internationally. More and more of these weather stations, and I'll put weather stations in air quotes, because if it's a weather station, it is a big complex with meteorologists running back and forth with printouts and so forth. Here in this case, what the weather station actually is, it's a series of probes probing the atmosphere. With these automated weather observing systems, you don't have to have somebody be out there to record the Tmax and the Tmin. And they're getting a lot of the information by just sensing the atmosphere and sensing atmospheric electricity for a lot of these things. All right, we looked at those. And also, when we discussed hurricanes, data buoys that collect data out at sea. And there's a picture of the good old data buoys. Remember radio sounds? All right, that's a pretty important concept. A package of instruments that's carried aloft by a weather balloon that gets a temperature profile of the temperature profile, a humidity profile, and a pressure profile, and when tracked from the ground, wind speed and direction. See, meteorologists want to know what's the temperature profile. Is it declining with height? Is it not declining with height? Is there a surface inversion? Does it decline with height and then increase with height aloft and then decline with height again? All of these things will tell you something about the atmosphere and very useful in trying to predict the weather. Weather maps, of course. When you look at each individual weather map, if you have the lower 48 of the United States and one weather map for one particular hour, and if you were to put together a series of these, what you'd be doing is you'd be watching a movie, because each individual weather map is like one still frame in a motion picture. You know, when you're watching the motion picture film, it's a series of images that flash by you. All right, now remember, we call the weather maps that look at the lower 48 of the United States synoptic charts, synoptic weather map, which means coincident in time. Well, different parts of the atmosphere will tell you different things. So it's important not just to look at the surface chart, but also to look at the charts higher up. All right, for example, here the 850, all right, so you have to go up a little ways to find 850. That's good for showing where you have cold air advection, warm air advection coming in. At the 750 millibar level, you can get even a greater general pattern of it. 500 millibar maps are good for showing the upper level lows. And so this may predict what's going to happen at the surface, and also what's happening with the surface lows, because the surface lows are influenced, get swept around by what's going on in the upper atmosphere. All right, so here's the 500. And what if you want to see the jet stream? Then 300 and 200 millibar charts will illustrate where the core of faster flowing upper air winds are, the jet stream. Previously, I had told you about zonal versus meridional. Zonal meaning basically west to east, weather coming from the west, whereas meridional refers to up and down the meridians. Now, when you have a situation in the upper airflow that's basically zonal, you have kind of consistent weather every day, and depending on which side of the jet stream you're on, it'll either be warm or cold. But when you have a meridional setup, up and down the meridians, well, that can move warmer air down south, up north, and vice versa. Polar air can dip down further south. And this moves, this snakes around, but it also moves. The next day, this trough may be in this area. So what's going on in the upper air wavy flow has a great influence in understanding day-to-day weather. All right, there you might see a question in the quiz bank about meridional patterns are associated with the greatest day-to-day changes in comparison to zonal flow. All right, and these upper air winds have an effect of directing the cyclones and anticyclones at the surface. All right, well, if you get the question, what effects my high amplitude waves have? Well, you have a lot more day-to-day variation. And why do middle latitude cyclones so often develop to the east of upper level troughs? That's because there's when the upper air flow is undulating as the air goes around a curve. Okay, kind of like when I'm driving my go-kart, and I swing around, and you create a little bit of counterclockwise spin as I overshoot. So you have vorticity that's created east or downwind of the upper level troughs. Usually I like to have an in-class exercise where I have students look at a before and after station model. Now we've been seeing the station model on a lot of the example textbook weather maps, and we've been building things as we go along. The actual National Weather Service synoptic charts have a lot more symbols and a lot more potential numbers on there. We'll dig out a few. What I like to do for an exercise is to show the before and after a frontal passage. Okay, so what are we supposed to see here? I think from previous maps, you know that where they put the temperature versus the dew point. If the temperature is 57, the dew point is, well, that's pretty sticky. All right, that's humid air. The sky cover looks like it's clear for the moment. The wind speed and direction, now it's not always pointing that direction, so it means that it's a northwest wind. Now, what comes up, and it's kind of interesting that they still do it this way, but you have sea level pressure, 107. Well, that couldn't be 107 millibars, would it be? Well, yeah, here's what the convention is. What you do is you have to imagine you would put a 10 in front of that if the number was less than 500. So what the millibars there is 1010.7. Or you put a 9. If the three digits are greater than 500, then you put the 9 in front. And so it has to be reasonable. That's because with these National Weather Service synoptic charts, it's a jumble. So one way to save on space is to conventionally show pressure in that manner. And the experienced meteorologist forecaster knows to look out for that. This is the appendix figure that looks at more of the numbers and symbols that are put on the station model. Notice you also have symbols for weather conditions. Right, so look at a before and after, a frontal contrast. And we have been doing this throughout the course. All right, so in this case, you got, look at these two. Look at the difference in dew points as you go across, the difference in the wind direction as a cold front would be expected to pass over, clearing skies. All right. Numerical weather prediction uses mathematical models and produces prog charts. Progs or prognostic charts. Such as producing one such as this. What's an ensemble? Well, that's when a number of forecasts using the same computer model is utilized, but there's going to be some differences between each run. And so they say that it's an ensemble because it's by balancing all of those, what sounds the best. What's the butterfly effect? There's some different ideas about this, but basically it means that a little bit of variation early in the system can magnify itself out later. So the difference in one forecast model and another forecast model, well, if you just added in the flap of a butterfly wing, and that eventually over time that difference in air movement would lead to dramatically different conclusions, is one way of looking at that. Persistence forecast is pretty easy because you just expect that the weather will persist. For example, if it's raining right now, what's your forecast? Well, rain. Or if the pattern is set up that the rain is coming towards us, you would expect that that rain will persist, it will come at us, so you would forecast rain. Is climatological data used in forecasting? Well, it is, because you need to know basic characteristics of the climate, the long term, the average of what the daily high, what the daily low are, the sun angle, and so forth. All of those things are climatological. Now, you can't look in a climatological chart and try to predict the day's weather, but it's one other element of using the forecast. If you want to do climatological forecasting, well, you just base it on what usually happens. So, for example, here's my forecast for the weather on the 4th of July this year. Let's see, so for the 4th of July, it's going to be hot and humid and 30% chance of afternoon thunderstorms. See, there I'm basing it on the climatology. Here's another example of a climatological forecast. Remember from the precipitation chapter, the probability of white Christmas, meaning what's the probability of having at least an inch of snow on the ground on that day. And generally, we don't have to worry about it. North Carolina, we're not going to have a white Christmas. A lot of people in the Northeast, that for them, the traditional Christmas, it's you have snowfall on the ground. All right. Analog, well, let's see, the analog method would look at, well, things have occurred in the past and then this happened. And so if you look at the current map, and then you ask yourself, if you look back through all the other old weather maps, or if you use pattern recognition to figure out what it looked like, and then think, well, in the past, this low moved in this direction when the high was over here, and so forth, and use that as an analog. Trend forecasting is another way of trying to extrapolate from the weather phenomena. How about the use of satellites? It's been invaluable in making forecasts much more accurate than they were before 1960, when I think those cartoons were probably a little bit more meaningful. What's the difference between polar orbiting and geostationary? Well, the ones that are polar orbiting, they're orbiting the poles as the Earth rotates underneath. And so what they're doing is they're scanning the entire Earth, not at once, but a little bit at a time, and you get the entire Earth. Whereas geostationary satellites are usually further back, and they stay over one particular area. Look at the weather there, which is what I'm telling you right now. All right. Here's an example of some satellite imagery. And let's see, on the right-hand side, it's kind of interesting. You see those cumulonimbus clusters? They're overshooting tops into the stratosphere. All right, what's the difference between visible and infrared? Well, with the visible light, you have to have the sun out. The visible light, you can get a higher resolution picture. You're not going to get temperatures. With infrared, it's good at, well, you're measuring long wave radiation. You're measuring the temperature of things. And the idea is you have storm clouds are going to be cooler. Well, that would be the opposite of what you might expect. Storm clouds have more energy, be warmer. The way it works is that, well, the higher clouds, the top of a storm cloud, that's very vertical in its dimension, will have a cold top. So if the first thing the satellite sees is something cold, then that means that's a high top of a cloud, a high thunderstorm cloud. Water vapor images are also good to see what the possible precipitable water will be. Here you can see the difference between the dry areas shown in black and then the lighter areas with more moisture. And once again, here's another example of the infrared. And the bottom diagram is a color-coded image to help us reasonably see where you have the most intense convection and the strongest storm. Under types of forecasts, what's the difference between qualitative and quantitative? Well, qualitative is a quality. You're explaining it in everyday languages. So, for example, qualitative versus quantitative temperatures. If you say qualitatively it's warm in the room, that's qualitative. Or if you said quantitative, if you said it's 76.5 degrees Fahrenheit in the room, then that's numerical. So it's quantitative. And here's an example of a quantitative forecast that has the precipitation in estimated inches. And that can be converted into a more qualitative map, such as that shown at the bottom. Here on this one, it looks at the probability of precipitation. You have a number on that. It's the percent probability where to get the most intense precipitation. And then you can also see where you're going to have the severe thunderstorms highlighted in yellow on the bottom map and the flash flooding that would result from that to be predicted. What types of forecasts are there? Short range, medium range, and long range? Well, the shorter the range, the more accurate you're going to be, just because things change. Medium range, 3 to 7 days, are still usually pretty accurate. Beyond a week, though, it becomes increasingly not accurate. How about long-range forecasts? If you're planning a vacation, you plan vacation based on what its climate is. Now, there are climate predictions that has 30 and 90-day outlooks. This just looks, though, that will the climate in this area be warmer or colder than usual or wetter than drier. It's not going to be precise. Is the woolly bear able to predict the severity of the winter? Well, this is a folk legend. And so for the larva of the Isabella tiger moth, the size of the brown stripe indicates whether or not it's going to be a mild winter or a severe winter. You have to wonder how the caterpillar is able to sense this. All right, that's all in good fun. Percentage probability. All right, you see this all the time. If they say there's a 40% chance of rain today, what does that mean? Well, there's a 40% chance that rain will occur at any given point in the area. All right. Types of forecasts, watches, and warnings. Well, when there's a watch, it usually means conditions are right. When there's a warning, that means that severe weather has developed, and you better take cover. You better get ready for it. All right, I've included the links for the Storm Prediction Center and the National Hurricane Center. Well, what does the forecaster do? Forecasters produce site-specific forecasts, and using their experience and also extra detail from their knowledge of the local area. What's meant by the term forecast skill? It's possible to be accurate, but not necessarily have the skill. For example for Los Angeles. Los Angeles has precipitation only 11 days each year, or 3%. So if you forecast no rain, you'd be accurate more than 97% of the time. But you wouldn't have any skill in that. Basically, what you're doing there is a climatological forecast. Okay, that's pretty much what we could do, I think, in here in 2460. If you want to take more advanced class, then we'll take a look at what a Ch12 is. That's looking at the radio sound data and looking at the temperature and moisture profiles and using that to better understand the weather. All right, we won't put the Ch12 on the final exam. Here's an interesting question for a student project, perhaps. How much rain does it take to make a rainout in baseball? Or what type of weather is likely to cancel a baseball game? And what are the rules on that? I have some links once again. Okay. All right. So this chapter has a lot that we've covered in some of the other chapters, and that's mainly where I'll derive the questions.